Abel's limit theorem is very useful. It can be used, for example, in the analysis and state classification in discrete time Markov chains. We have a sequence g of n, where n is a non-negative integer. We have the generating function g of z, which is this summation, g of n z to the n. Z is generally complex valued, but we focus here on z being real, or specifically z is greater than or equal to 0 and is strictly less than 1. So z is non-negative, and the magnitude of z is strictly less than 1. We have two parts. In the first part, if this summation of g of n is a finite number L, then if we take the limit of the generating function g of z as z approaches 1 from the left, then this limit is exactly equal to L. The second part, now if g of n is real valued and non-negative, and suppose that the limit of the generating function g of z as z approaches 1 from the left is equal to L. L can be finite or infinity. In this case, the summation g of n is exactly equal to L. And so if this limit is infinity, is plus infinity, this summation is plus infinity. If this limit is a finite number L, then this summation is a finite number L. Suppose that the summation is finite. Now define d of n as the summation g of r starting from n. So note that d of 0 itself will be summation r from 0 to infinity g of r, and this is exactly equal to L. D of n for a general n is basically the summation of the g's starting from n. So we can write d of n as the difference of the total sum, so the full sum with all the terms, and then we subtract the summation g of r from 0 to n minus 1. Note that this is a finite number, and this other term, as n tends to infinity, this other term will tend to L, and so the difference tends to 0. D of n goes to 0 as n tends to infinity. And because d of n, or the limit of d of n as n tends to infinity, is 0, then for every positive epsilon, there exists a big N, which generally depends on epsilon, such that for every small n greater than or equal to n of epsilon, we have the magnitude of d of n less than epsilon. Again, because the limit is 0, it means that for n that is large enough, the magnitude of d of n can be made arbitrarily small. In the proof, we will study the difference between L, which is this summation, and the generating function, which is this summation. Here we are summing g of n, here g of n times z to the n. And we want to make sure that both sums are finite so that we can combine them. So our assumption is that the summation g of n is L, which is finite. What about g of z? Well, if this summation is finite, then it must be that the nth term tends to 0 as n tends to infinity. And if the limit of g of n as n tends to infinity is 0, then for every strictly positive eta, there is a big K, which generally depends on eta, such that for every n greater than or equal to big K, the magnitude of g of n is less than eta. So again, it's another, like above, there is a limit that g of n tends to 0 as n approaches infinity. So this means that for n that is large enough, we can make the magnitude of g of n less than any arbitrarily chosen positive eta. Now suppose that you will sum the magnitude of g of n times z of n. Note that z itself is chosen here to be non-negative, so we can also put a magnitude here. So the sum of this magnitude, starting from k of eta, this summation, because we are starting from this value of small n, then the magnitude of g of n is upper bounded by eta. So we can upper bound the terms here by eta and take eta outside. We are left with this sum. Since z is chosen such that the magnitude of z is strictly less than 1, then what we have here is a convergent geometric series. And so we can sum it. And we get a result that is finite, which means that this summation here, if we start from k of eta, this summation is a finite number. And so if we start from 0, we will also get a finite number. So it means that this g of n, z of n, if we sum the magnitude, then we get a finite sum. So the series converges absolutely. And so this series converges. The summation n from 0 to infinity, g of nz to the power n is a finite number. So indeed, this L is finite by assumption, and consequently, this g of z is finite. We can write down the two sums, and there is no problem whatsoever in combining them. These are both finite numbers. Now, we take this summation here and we split it into two sums, one to v, from 0 to v, and the other from v plus 1 to infinity. And v is chosen to be equal to n, big N of epsilon over 3. So let's remind ourselves what is big N. We defined d of n as the summation of g of r starting from r equal to n. And we discovered that the limit d of n as n tends to infinity is 0, which means that for any strictly positive epsilon, there is a corresponding big N such that whenever small n exceeds or is greater than or equal to big N, this magnitude is less than epsilon. So we will choose v to be n of epsilon over 3. Okay, so by doing this choice, something, for example, that like the magnitude of d of v, this will be less than epsilon over 3. The magnitude of d of v plus 1, this will be less than epsilon over 3, and so on and so forth. So we go to this summation, we do a split here from 0 to v, here from v plus 1 to infinity, and I will write down g of n in this second summation as d of n. So d of n is equal to g of n plus g of n plus 1 plus g of n plus 2 and so on. D of n plus 1 is g of n plus 1 plus g of n plus 2 and so on. And so the difference between these two is g of n. Now we can split this into two sums. So one here, I will take d of n with 1 minus z to the power n, and then the other summation, n from v plus 1 to infinity, d of n plus 1, 1 minus z to the n, but I will rename the summation index as m. Now in this summation here, we will do a change of summation index, m plus 1 is equal to n. And this is done so that this d of n plus 1 is changed to d of n, and then we can combine these two sums again. So put m plus 1 is equal to n, and so this means that m is equal to n minus 1. So when m is equal to v plus 1, then n is equal to v plus 2. When m tends to infinity, n tends to infinity, and m itself here will be n minus 1. And the new summation will start from v plus 2. So go to this summation here and isolate the term with small n equal to v plus 1, so that we have dv plus 1 times 1 minus z to the power of v plus 1, and then we have a summation starting from v plus 2 to infinity d of n1 minus z of n. And this summation, after doing the change of summation index, now is summation n v starting from v plus 2 to infinity d of n 1 minus z to the n minus 1. Okay, so after doing these manipulations, basically what we have the original summation here, but we take it from 0 to v, here it is, and then we have two other terms, d of v plus 1 times 1 minus z to the power v plus 1, and then we have a summation from v plus 2 to infinity, d of n, and then we have z to the n minus 1 minus z to the power n. Okay. And now we have the magnitude of all of these three terms. We can apply the triangle inequality, and so the magnitude of the sum is less than or equal to the sum of magnitudes. And whenever we have the magnitude of this summation here or the magnitude of this summation here, also we can apply the triangle inequality. The magnitude of the sum is less than or equal to the magnitude of the sums. Note that this quantity here is 1 minus z to the power n, and z is between 0 and 1. So this quantity is non-negative. If it is real value, then non-negative. If we take its magnitude, then it is itself. And the same is true for here. And the same is true for here. Note that because z is a number between 0 and 1, then z to the power n minus 1 is greater than or equal to z of n. Okay, because z again is living between 0 and 1. And so when we take the magnitude of this term or that term or that term, we get the term itself. So apply the triangle inequality, and then we have an upper bound now on this difference here. Don't forget that we want to show that the limit as z tends to 1 from the left is equal to L. So the idea of the proof is to show that by choosing z to be close enough to 1, we can make this difference smaller than any arbitrary positive epsilon. Okay. So now let's upper bound this upper bound on the difference between or the difference of the magnitude of the difference between L and G of Z. So here basically this term is upper bounded by 1, and because of our choice of V, the magnitude of dV plus 1 is less than epsilon over 3. Now in this summation here, the index n is v plus 2 or v plus 3 and so on. So the magnitude of d of n is again less than epsilon over 3. And so we can upper bound by epsilon over 3 and take this outside. And then we have a telescopic sum, and the telescopic sum is equal to z to the v plus 1, which is less than or equal to 1 by our choice of the range of values of z. So this means that basically this term is upper bounded by epsilon over 3, and this other term is upper bounded by epsilon over 3. What about this term? Now for this term, we can, upper bound the magnitude of g of n by the maximum. So this is less than or equal to the maximum 0 n to v of magnitude of g of n. So we basically replace those guys by their maximum value. And then we can take this maximum outside. We are left with a summation n from 0 to v of 1 minus z to the n. Now in this summation, we have v plus 1 terms. And what about 1 minus z to the power n? This, when n is equal to 0, this is equal to 0. When n is equal to 1, this is 1 minus z. When n is equal to 2, this is 1 minus z squared. Note that z is between 0 and 1. And so as we increase n, z to the n gets smaller, and 1 minus z to the n gets larger. And so we can upper bound by basically 1 minus z to the power v, which is the highest value of n here in this summation. So an upper bound on this summation here is basically the maximum of the magnitude of g of n, n from 0 to v, times the number of terms, which is v plus 1, times the biggest guy here, which is 1 minus z to the power, the highest value of n possible, which is v. So the overall upper bound now is epsilon over 3 plus epsilon over 3 plus this quantity. The question is, if we want this magnitude, the magnitude of the difference, to be upper bounded by epsilon, for any given positive epsilon. Can we do so by choosing Z, close enough to 1? Yes, we can make this term here less than epsilon over 3. So just take this term, make it less than epsilon over 3, and discover that by choosing Z, so Z is of course less than 1, by choosing Z to be greater than this quantity, we are able to make this less than epsilon over 3, and so the upper bound is epsilon. Okay, and this quantity here is a number less than 1. It is 1 minus something to the power 1 over V. Don't forget that V is n over epsilon over 3. So chosen so that magnitude d of n with n greater than or equal to V is less than epsilon over less than epsilon over 3. Okay, so that's the V. And then here we have epsilon over 3, and we have here the maximum of those. Guys, this is the number. I mean, knowing the sequence g of n, we can compute this. So challenge me with an epsilon. Once epsilon is given, we can determine V. And once we know V, then we can find the maximum of the magnitude of g of n from 0 to V. And by choosing Z to be greater than this quantity here, this term will be less than epsilon over 3, and the overall upper bound is less than epsilon. Okay, so that's it. What we have just done is that for every strictly positive epsilon, there exists a Z tilde, and of course this Z tilde will generally depend on epsilon. And Z tilde, as we can see, it has, it has a range of values, so it should be strictly less than 1 because we choose Z to be strictly less than 1, but Z tilde should be greater than this quantity here that we obtained by making this quantity less than epsilon over 3. For every Z that is greater than or equal to Z tilde, and Z tilde is sufficiently close to 1. It is less than 1, but greater than 1 minus this quantity, all raised to the power 1 over n of epsilon over 3. Then for every Z greater than or equal to Z tilde chosen in this range, we can make the magnitude of the difference, g of Z minus L, greater than epsilon. And this is exactly the definition of this statement, that limit g of Z as Z approaches 1 from the left is equal to L. So this is the first part of Abel's limit theorem. Now suppose that g of n is real valued and is non-negative, and suppose that the limit of the generating function as z approaches 1 from the left is L, where L now is also allowed to take the value plus infinity. Now the summation n from 0 to infinity of g of n, note that g of n now is greater than or equal to 0. So this summation is reduced in value if we replace the 1 that is here by z to the n, because as above, we have z in this range. So g of n is greater than or equal to 0. It's multiplied by 1. So I can lower bound this summation by g of n multiplied by z to the power n, given our choice for the range of values of z. Now, when we do so, this summation here is exactly the generating function. Now we have that summation n from 0 to infinity, g of n is greater than or equal to g of z. So take the limits of both sides as z approaches 1 from the left. Now, the left-hand side here is not a function of z. So you can take the limit. Okay, so limit z approaches 1 from the left. And here we do the same. But this guy does not depend on z. So the limit is this quantity, which is this summation. And on the right-hand side, we have the limit. And this limit is L. Suppose that the limit is indeed equal to infinity. So in that case, this summation here is lower bounded by infinity. So this summation of g of n, which in our case is real valued and non-negative, must be plus infinity. So this is the situation in which the limit of the generating function is infinity. What if the limit is finite? In this last case, we will take the summation g of n, n from 0 to some big N. Now we have a 1 here, and we can replace this one by the limit as z approaches 1 from the left of z to the power n. Now we have a limit inside the summation, but the summation has a finite number of terms, and limit is additive, is linear. So limit of a sum, a finite sum, is the sum of the limits. So we can take the limit outside. We can take the limit outside. So this summation here is exactly equal to the limit as z approaches 1 from the left, summation n from 0 to big N, g of n z to the power n. Note that z is non-negative, g of n is non-negative, and so you can upper bound this summation by having more terms. We are adding non-negative quantities, and so we get a higher sum by having more terms. So this summation here is upper bounded by the full sum going to infinity. So this summation is upper bounded by the case in which big N approaches infinity. This summation is the generating function. So for every n, for every big N, what we have is that summation n from 0 to big N g of n is upper bounded by the limit z approaching 1 from the left of the generating function g of z. This is true, and this guy now is equal to big L, and we are investigating the case in which big L now is finite. We already have established that if big L is plus infinity, then this summation is plus infinity. Now the interest is in the case in which big L is a finite number. So this sequence is bounded above by the finite number big L, and this sequence, because we are summing the non-negative values g of n, then by increasing n, this summation is monotonic. So it is non-decreasing. And so using the monotone convergence theorem for sequences, so think of this as a sequence in big N. It is monotonic, so this sequence is non-decreasing, and also it is bounded above by a finite number. So the monotone convergence theorem for sequences will tell us that this sequence, as n tends to infinity, will converge to a finite number. Okay, so this sequence, there is convergence here. Now the upper bound is equal to L, and so convergence will be to L tilde, and L tilde is less than or equal to L. So we cannot say that convergence will be to L. However, if summation n from 0 to n and then limit n tends to infinity, g of n is equal to L tilde, and L tilde is finite, then by the first part of Abel's limit theorem, which is this part, if this summation is equal to something that is finite, then the limit is equal to the same quantity. So if this summation is, if this statement is true, then limit of g of z is equal to L tilde. But we take it that the limit is equal to L, then L tilde is equal to L. And so now we have established the second part of Abel's limit theorem, which is if the sequence of interest is real valued and non-negative, and then we evaluate this limit here of the generating function g of z as z approaches 1 from the left, then if this limit is plus infinity, this summation is plus infinity. If this limit is a finite number, this summation is a finite